Okay, we're going to do a little bit of review here. We're trying to talk about logical inference. We've done two different ways of doing it. We're going to introduce a third, but before we go ahead with the third one, I would like to review the first two. So I want to imagine we're given the following premises. I'm told that statement A is true, and I am also given that I'm not given not A or B, and I am told that not C implies not B. And from this, I would like to determine if I can infer statement C. And let's remember the first way to do this is with a truth table. And what we're doing here is we are going to construct a truth table, A, B, and C. And then what we'll do is we'll repeat the premises here, which is A, not A or B, not C implies not B. And then the actual conclusion here is C. And we see that we have 8 rows here. Okay, so in this first row here, I'm just going to repeat the column I have from A. Okay, so let's consider this over here. Now, first of all, we know that this statement over here is true whenever B is true. So wherever I see a true for B, I'll come over here and write a true. False, false, true, true. And then the other time that this is going to be true, let's see, it's true whenever not A is true. So it's going to be true whenever A is false. So I've taken care of 2 of those already. So it's going to be true over here. And it's going to be true over here. And these then would be when this statement is false. Okay, so let's think about the implication here. We know that this is false whenever this is true and when this is false. Okay, so not C is true when C is equal to false. And not B is false whenever B is equal to true. Now remember what we're doing here is we're just finding the situations where this is false. In all other situations, it's true. So it is, let's repeat that one more time. This statement here will be false when C is false and B is true. So I come over here and when B is true and C is false, so it's going to be false over here. When B is true and C is false, it is false over there as well. Okay? In every other one of these situations, this statement's going to be true. So I come over here, true, 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 and true. And now what I'm going to do over here is I'm going to come over here and I'm just going to repeat column C. and I get false, true, false, true, false, true, false, true. Okay, we're ready to make a conclusion here now. Remember what it is that we're trying to do is we're trying to say whenever these three statements are true, is it always the case that this is true? So I've got to come over here and look for the situation where these three statements are true. And it looks like the only time that happens is right down here. And notice that when these three statements are true, when the premises are true, then I have that C is true, the conclusion is true. So my conclusion here is that this is valid. Let's consider the same problem again, but now we're going to prove the inference in a different manner. This one is going to be called a proof by contradiction. And we've already seen this. We're just doing this again for review. And again, our premises were A and not A or B. And then we had not C implies not B. And we're trying to prove that this implies C. Now remember, we said that this can be written as one very big implication. And over here, we have A and here's the big implication over here. So what we're saying is that this and this and this implies C. And what we do here is we try to derive a contradiction. So what that means is we come over here and we say, let's suppose that the contradiction is false. Now, if the contradiction is false, that means that everything over here on the left is true and everything over here on the right is false, namely our conclusion C. Now, if everything over here on the left is true, I'm going to write a true under each one of these and signs. Remember what that means. It means that this is true, and this is true, and this is true. Now, let's start investigating a little bit more. Now, if this is true, that means that A must be true. And I come over here, if A is true, then not A must be false. And remember, this entire expression over here has to be true. Well, if I've got a false on one side of an or statement, the other side better be true or I'm in big trouble. So this has to be true. And I come over here now, let's see, C is false. If C is false, then not C has to be true. And again, we remember that this thing over here, this implication, okay, it's one of our premises, so this has to be true. Okay, and we know that if I have an implication that is true, and the left side of the implication is true, the right side of the implication has to be true. Okay, if this were false, then I would have true implies false, and we know that's not true about a true implication. So this would have to be true as well. But now take a look at what we have over here. We have over here that B is true, and we also have that not B is true. That's a contradiction. Now we derived this contradiction by assuming that our original implication is false. So our conclusion is that the main implication is true. In other words, this is incorrect. And the conclusion here is that the argument is valid.
Hey, kids, let me tell you about something that happened here at the ranch the other afternoon. It was just about dinner time, and Dale and I were just getting back from town. In fact, we were late, and Dale was worrying about making supper, so she jumped right out and hurried inside. And when she got inside the kitchen, she found all the kids making dessert with Jell-O instant pudding. Dale was just as proud as she could be, and they sure whipped that pudding up quick and easy, too. You know, with Jell-O instant pudding, you just empty the package into a bowl that has some cold milk in it, and then you beat it up. There's no trick to it at all. And kids, you just never ate a better tasting dessert anywhere, whether it's butterscotch, vanilla, or chocolate. So ask your mom to get some Jell-O instant puddings for you real soon. And then the next time she's busy, you can have the swellest dessert in the whole world all ready for her. Don't forget the name. It's Jell-O instant puddings. And now, how about singing the Jell-O instant pudding song with us? You ready?
Sure are.
Okay, here we go. Oh, it's never too late to make dessert with Jell-O instant pudding.
So get the busy day dessert.
Jell-O instant pudding.
It's so easy a kid can make dessert
With Jell-O instant pudding.
So get the busy day dessert.
Jell-O instant pudding. Yep, you get some Jell-O instant puddings in all three flavors. Vanilla, chocolate, and butterscotch. They're good.
So now we have a third method for determining logical inference here, and I'm going to call these the direct proofs. And before we can actually do a direct proof, we have a few other things to talk about. There are various rules of inference that are available to us, and we should take a look at these right now. So I want you to consider the following. Suppose that I'm told that statement P is true, and I am told that P implies Q. We've actually proven this if you go back and look at some of the previous videos. But I think you'll believe that if this is true, and this statement is true, then I am able to conclude Q. You can verify this with a truth table, and this is a very important rule over here, and it actually has a name. It's called modus ponens. Okay, there is another very important rule here, and we have a few of these that we have to go to. If I were to tell you that P implies Q, and then I am also telling you not Q is true, the conclusion here would be not P. And again, that has a name. Modus tollens. And again, I would ask you to go ahead and verify this via truth table. Some of these are very obvious. If I were to tell you that P is true, then I can conclude P or Q. Okay, if I have a true statement, I can OR it with anything and I still have a true statement, because remember, for the OR to be true, only one of these has to be true, and we already are known that P is true. This is what is sometimes referred to as OR introduction. Here's something that should also seem very obvious to you. If I were to tell you that P and Q is true, I could certainly conclude that P is true. This is sometimes referred to as AND elimination. Okay, let's think about what we can conclude here. If I were to tell you that P or Q is true and not Q is true, we'll come back up here and think about that. If not Q is true, then Q is false. So the only thing I can conclude over here is that I must have P. And your book calls that elimination. I have another name for it. It's called refutation. Okay, and the last one should seem very obvious to you. If I were to tell you that P implies Q, and then I were to tell you that Q implies R, we can come over here and we can conclude that P implies R. And this is called transitivity. Transitivity. T-Y. Okay, so we have 1, 2, 3, 4, 5, 6 rules of inference here, and in a moment we'll use them to solve a problem. Okay, let's put this all to practice now. Let's imagine the following situation. I'm about to go to work and I can't find my glasses. I do need them. Okay, so I want you to consider the 5 statements here, A, B, C, D, and E. And I say the following. If I was reading the newspaper in the kitchen, then my glasses are on the kitchen table. And what I want to do is I want to symbolize this. So I'm going to let RK equal the statement, I was reading the newspaper in the kitchen. GK is the statement, my glasses are on the kitchen table. So what statement A is really telling us, technical glitch here, excuse me. All right, I see the problem. Okay, so what statement A is really saying to us is that RK implies GK. Okay, I hope that's clear. Statement B says, if my glasses are on the kitchen table, then I saw them at breakfast. So I'm going to introduce a new symbol here, SB. I saw my glasses at breakfast. So what statement B is telling us, if my glasses are on the kitchen table, GK, Then I saw my glasses at breakfast, SB. Now I want you to notice something right away just between these two statements here. I have RK implies GK, GK implies SB. I can come over here and I can conclude that RK implies SB. This implies this. This implies this. If you go back and look at our rules, that's by transitivity. Okay? Now I come over here. I did not see my glasses at breakfast. So I come over here and I say, see? And I did not see my glasses at breakfast, so that would be not SB. And now I want you to notice something. We have that RK implies SB, and we have not SB. I can come over here and I can conclude not RK. Okay, and why is that? That's modus tollens. Okay. I was reading the newspaper in the living room, or I was reading the newspaper in the kitchen. So I come over here and statement D is telling us I was either reading in the living room, RL, or RK. Okay, but notice the following. I've already derived not RK, and over here I have RL or RK. So I can make a conclusion over here, RL. And if you go back and look at the rules, that is by what's called elimination. And then I come over here. E says, if I was reading the newspaper in the living room, then my glasses are on the coffee table. So that statement E would be translated as RL, then GC. Okay, and notice what I can do over here. RL and RL implies GC allows me to conclude the glasses are on the coffee table. Okay, and this rule over here was modus ponens. This is what's called a direct proof. Okay, you should study this and do your homework. More later.